Good morning. My name is Bjørn Nordmoen. I'm working with Schlumberger Western Geco. In this presentation, I will present the work we did as part of the EMC2 program, where we developed a tool called m2cpp that is a code conversion translating tool that translates MATLAB code to high-performance C++ multi-core code. This work was done as part of VP12, use case 12.1. This is my presentation outline. First, I will talk a little bit about the business context, presenting Western Geco, what we do. Then I will go through briefly the current engineering process, how we work today, and I will run an example of a MATLAB test program from the seismic lab demo, and talk a little bit about the main challenges we have. And finally, I will talk about the new optimized engineering process, where we use the new m2cpp tool to convert the MATLAB to efficient high-performance C++. I will show you several steps here. Just plain generation, then with type recognition, and then also with generating parallel code, and finally show you some timing values. Okay, Western Geco is a company owned by Schlumberger. We are the segment that do seismic acquisition. That means we work with inland and marine, and in this context here, we are talking about the marine seismic, where we have boats towing big arrays of sensors behind. Might be 10 strings of streamers, each about 10 kilometers long, and with 20,000 sensors in each streamer, sending sound waves into the earth and measure the reflection. So in one sense, it's kind of taking a picture of the underground using sound instead of light. This is very big and complex system, and the data rate is about 1 gigabit per second per streamer coming into the boat, and all this data has to be signal processed in real time. That means very complex algorithms that needs to go very high speed. Okay, here I show a video from a field operation outside Australia. And here you have one of our special designed boats towing 10 streamers, I think. They use floating devices like troll doors to get the wide separation. And behind the vessel, you tow an array of air gun. Here we see the floating devices for the air gun. The air gun sends the sound into the earth, and the streamers behind the boat with the sensors measuring the reflection. So now I will talk about our current engineering process, the way our researcher works today. What our researchers do is that they normally write the prototypes of the algorithms in MATLAB. This is the tool they prefer. In that sense, they can focus on the algorithm and not really on the details of the underlying hardware, multi-core or whatever. Of course, then to industrialize this, that means to put together an engineering process to transform it to more industrialized production code is very time consuming. So the main challenge is really that we need to shorten the time to bring these new algorithms from research to production. And also, as we get more and more data and more complex algorithms, the need for performance gets higher and higher from year to year. You might ask, why do we really need to develop this tool? Why can we not just buy a tool, or maybe MATLAB have a tool? And MATLAB have something called MATLAB Coder that takes MATLAB into C. The reason why we cannot use this tool is that this tool is mostly for portability. I mean, you can take your MATLAB code and get it into C so you can run it in an embedded device. This is not a very performant tool or code, and what we need is really high performance execution. So that's why we have made our own tool, so we can integrate with MKL and other high performance libraries. Okay, next now I will just run a MATLAB example for you. And this is the example we will also convert and show the high performance C++ version. I will now show a demo of a typical MATLAB program. This is from a public domain package called Seismic Lab. This is the one I also will use for the showing the optimization code generation process later. So this is a seismic algorithm called parabolic move out. Yeah, that looks at the what we call the residual movements after we're doing an NMO. And this program consists of four different parts. It reads a data file, then there is a parabolic move out function and a normal move out function, and there is some plotting functionality. And as you can see here, yeah, it reads the file, it calls the normal move out, and it calls the parabolic move out. The normal move out again is described here, typical MATLAB functions. And here is the parabolic move out. And you can see there are quite a few for loops in these programs that can be probably optimized later on. And then I run my parabolic move out program. So it read for the 49 traces of a small data set. It produced some plots here, and you saw the time was about 3.9 seconds for this. Okay, so now we are coming to the core of this presentation or video, where I'm going to show you how we have optimized our engineering process and how we use the m2cpp tool to help us generating high performance code from MATLAB. So the code is it can be found on the GitHub under this URL. What you need to do is to go there and download the code, install it, and when you have done that, you need to run a Python installation script like this syntax here. So let's go and do that. Okay, I have here a console where I have gone into the folder where I installed or downloaded my program. You will see here the setup program, the package info, the MATLAB to CPP, the manual, yeah, various programs. So what we need to do now is to install the code. I already done it, but basically what you do is this: Python setup install. This will install it properly and also make the path and everything okay, so you can run the m2cpp. So let's see on the help file here. You see this is version 1. It has a few arguments. The main one I will talk about here is the -o original. This one generate code, includes the MATLAB code above the generated line, so you can see how the translation works. There is another one I will talk about later, -uppercase S. This is a one that in fact runs the MATLAB program in the background as part of the code generation in order to get a better understanding of the types. And then there is a flag for the parallel generation, OpenMP or TBB. There is also a ref if you would like to have parameters go by reference. This is also important for big data types and optimal speed. So let's now try to run a conversion. I first need to go into where I have my code. It's here. It's in the it's this MATLAB file here, parabolic mu demo. I would like to run. I already rerun it. That's why there are some other files here now, but we can just ignore that for now. So m2cpp. I wanted to have the MATLAB code showing. I like to clean up the temporary files I made. So there is a clean generation, and then my program. And you see it only used a few seconds on the generation, and now I would like to watch it. I have the files here in a Crimson editor, so that was refreshed. So basically this is the file. You see it was generated now. Here is the time tag, and what you can see here is that it figures out the other dependencies. It does something funny here because it does not really figure out all the types. This when you run it like this, the code try to do a static, or the converter try to do a static analysis to figure out the types, and it did not understand all these types here. It understands a few others, and you can see here the code is quite simple. Here is above each generated line there is the equivalent MATLAB line, so you can see how it maps. And you also can notice here what I haven't talked about, that we also have some pretty simple generation of plotting. So if you don't have too complex plotting in your MATLAB program, we have made an interface using Python, in fact, to simulate the MATLAB plotting functions. So, but this you can turn off. And also the tick here is tick-tock for timing that you can use in MATLAB. Is also here generated into equivalent function in C++. What is interesting is that in parallel to generating the code itself, we also create what we called a type file that has the same name and the extension .py. And here is the type file that was generated, and as you can see, it had some problems to identify the types by static analysis. This is what it found out, and here is the include files. So what we need to do now is to rerun it with some improved settings, so we can find more types. Another thing here is that we're also using some special function here. Read seg_y is quite different in C++. So this function we have in fact written ourselves in C++, because the I/O and complex I/O is not easy to translate directly. So then we have a substitution function in support. So you can go into the type file and kind of highlight that this line I like to substitute with something else. So this is the next thing I like to show to you, how we can substitute new values here. So I have another file here. We've already done this. It's called verbatims, and then I go in here. So what you can see here, we substitute this line here. This line here is substituted with this, and also this line here is substituted with this thing here. So So I will just put this into my Py file here. And then I will rerun my code generation. And now I don't want to reset. Don't want to reset it. And now we can go back and we can see in the type file now we have this included. If you look at the generated code, we will see here now that we have at least got the seg y reading correct, and we get this loop here correct now. Then the next thing to do is, because we are missing a bunch of types that we like to see if we can understand. So we will like to run the program with the substitution working. So then I need to put in two things. First, I also need to put in the path, this set path program. So because now it has to run the MATLAB, in fact, in background, it needs to understand where to find all the files. So I include the set path. Then I include the uppercase S for full type substitution, and then I have my program here. And let's go. Now it will take longer time because it has, in fact, to start MATLAB in the background and run through the program. So what we do then is that we inspect in runtime and figure out the types by dumping the internal state of MATLAB as we go along. Okay, so here it was. So let's go and have a look again, and you see it has to refresh the files. So let's see how it looks like now. So here is our program, and now you see the types has been figured out. Then the next test is, in fact, to see if we can also now run this with the parallel TBB execution. So if you look into the into the code here, you will see that we have in front of various for loops, we have this tag here called par4 as a comment, so it's normally ignored. And so in the parabolic move out, there is a double for loop, and also in the NMO, there is a double for loop. So remember, so here is the code for the parabolic move out. There is no parallel code here. So if you now go back to our generation here, now we don't need to run the type system anymore. We can just run -TBB. Yeah, if you look at the code here for the NMO, you see we have now got generated code here for the TBB stuff. And if you look at the parabolic move out, we will have the same here. Yeah, so these are quite complex or structure that is now auto-generated for you. When it comes to the main program, there was no parallel loops here. So let's go and run this code. I think I have demonstrated now the various options I planned. I show you how to download and install the code. I show you how to run a plain generation. Then we use with the O flag, you can see the MATLAB code inserted, so it helps readability. And I also did with the path option and the -s. That means that you can find out most of the types. You can do substitution using verbatims and substitute certain code which you want to do different than the MATLAB. And then finally, by using the TBB, you could also generate the parallel code. So let's have a look at that. So here is Visual Studio. I have already uploaded the code here to the Visual Studio, and let's have a look at the main code here. As part of this code, I can define how many cores I would like to run. So in this case here, I have put it to 1 core. So let me build it for 1 core. Okay, and then I will run it. Okay, so you can see that with 1 core here now, it produced the graphs and it says it used 0.6 second. Remember the MATLAB says 3.9, so it's already quite a lot faster. So let's go in here and make it 8. And then we run again. And now it ran on 0.1. So this is quite fast. So it's a quite good improvement then from MATLAB from 3.8 to 0.1. So this brings me to the conclusion. What we have seen is that the code generation shortens the engineering time dramatically. In our case now, it took only a few minutes. This is work that normally will take days or maybe weeks to do by hand. Number 2, what we also have seen is that the generation of the parallel C++ program running on multi-core improves the runtime performance significantly. In our case, it went down from 3.9 seconds to 0.11. That means 35 times faster. But we also know by code generation here now is the code generation will have higher quality because it's based on the MATLAB original. And finally, since the generated code is similar to the MATLAB code, it's easier to understand and trace, and it also then can be used for further hand optimization, and also further improvement in the MATLAB is easy to map into the C++ code. So that was my presentation. Thank you for your time. And I would like to thank my co-workers here from Simula Research Laboratory and Fornebu Consulting for the good collaboration we have had on this project. Thank you.